Assalamualaikum. So today we will start with chapter 1 of Morse Manor, which basically covers the topics of digital systems, binary numbers, number-based conversions, and different base numbers, complements, subtraction using complements, signed binary numbers, binary codes, and registers, and a little bit introduction of registers and binary logic. So first we will cover up to the topic of complements. Then in the next lecture we will cover the remaining portion of chapter 1. So basically in today's technology age we are using digital systems everywhere. Digital systems are replacing the analog systems because of their fast speed and vector accuracy. As you know that there are better detection codes and there are specified levels in digital systems, so it's better to use digital system in spite of analog system because digital systems have specific values at discrete intervals of time, and error detection and correction is easier and they are fast as compared to analog systems. So we have all the devices in today's age which are digital systems. For example, your TVs, computers, phones, and etc. These are all examples of digital systems. So binary digital signal. Basically binary signal or digital signal has two specified values, a high value which is equal to logic 1 and a lower value which is equal to logic 0, and the portion between the logic 1 and logic 0 and between these levels, this is undefined. You cannot call it as logic 0 or logic 1. So you can call the logic 1 as a true value and logic 0 as false, or vice versa, or on off values. So the basic number system which you have learned so far is decimal number system, and decimal number system is of base 10 because it uses 10 digits in the number system from 0 to 9. So you can write a decimal number system as powers of 10. For example, this is a decimal number system and it has a number 512.74. It has an integer part and a fractional part. So you will multiply each coefficient with powers of 10. 2 multiplied by 10 raised to power 0 plus 1 multiplied by 10 raised to power 1 plus 5 multiplied by 10 raised to power 2, and on the fractional side you will write 7 multiplied by 10 raised to power minus 1 plus 4 into 10 raised to power minus 2. So when you will add up all these values, this will be equal to 512.74 in base 10. Next is octal number system or number system with base 8. It uses 8 digits from 0 to 7, and you can write an octal number as weights of 8. For example, if you want to convert any number system into decimal number system, you simply have to multiply the coefficients with power of the bases. For example, here you are converting the base 8 number into base 10 number. So you will write 2 multiplied by 8 raised to power 0 plus 1 into 8 raised to power 1 plus 5 into 8 raised to power 2 plus 7 into 8 raised to power minus 1 plus 4 into 8 raised to power minus 2. So this will be equal to, when you will add up all these values, this will be equal to 330.9375 in base 10. Next is the very common use number system in our computers and digital systems is binary number system. So the machine level language always uses the binary number system. So in binary number system there are two digits 0 and 1. So in binary number system, any number given in base 2 can be converted into base 10 by simply multiplying the coefficients with powers of 2. So you will write 1 multiplied by 2 raised to power 0 plus 0 into 2 raised to power 1 and plus 1 into 2 raised to power 2, which is equal to 4 in this case. So on the decimal side you will write 0 into 2 raised to power minus 1 plus 1 into 2 raised to power minus 2, which is equal to 1 by 4. 2 raised to power minus 1 is 1 by 2. So when you add up all these quantities, the value will be equal to 5.25 in base 10. Next is hexadecimal number system. In number decimal system, there are 16 digits from 0 to F. For 10 you will write A, for 11 you will write B, 12 is C, 13 is D, 14 is E, and 15 is F. So if you want to convert this hexadecimal into decimal, you will simply multiply these coefficients with power of 16 on both sides. So this will be equal to this decimal number. So powers of 2, because these are powers of 2 are important in conversion from octal to binary and hexadecimal. It shows how much number of bits we need in a binary system for a specific number system. So 2 raised to power 0 is 1, 2 raised to power 1 2, and up to 2 raised to power 7, which is equal to 128. So 2 raised to power 10 is kilo, and up to mega and tera. So decimal addition. As you know that for decimal addition you will simply add two numbers and there will be a carry in this case. So 5 plus 5 is 10, 0, 1. So simply using this rule you will have 110 as a result. Next is binary addition. So in case of binary addition, we suppose we have these two numbers 11101 and plus 10111. So starting from the least significant bit, 1 plus 1 is 2 and 2 in binary is 1 0. So you will simply write 0 1, 1 plus 1 0 1, 1 plus 1 plus 1 1 1, 1 plus 1 0 1, 1 plus 1 plus 1 is equal to 3 and 3 in binary is 1 1. So again 1 carry, again 1 will add in 1, 1 plus 1 0 1 1. So this is the number in binary after adding these two numbers. We have simply used the rule of addition and using carries. So binary subtraction is just like decimal subtraction. You have to simply take care of the borrows in this case. So for example, we have these two numbers. We have to subtract this number from this. 1 minus 1 is 0. Here is 0 minus 1. You have to borrow 1. 1 0 will be 2. 1 0 minus 1 will be equal to 1. Again you have 0 in this, left with 0 in this place. So you will take 1 as borrow. 1 0 minus 1 again 1. Now you have left with 0 0 minus 0 0, and again as we have 0 here, so simply you have to again take a borrow from this side because again there is a 0 here. There is a borrow from 1 1 0, again borrow from 1 1 0 minus 1 will be equal to 1, and now you are left with 1 here. 1 minus 0 is equal to 1, and now there is no 1 here. We have simply 0 minus 0 0. So binary multiplication is basically bit by bit multiplication, just like the decimal numbers. Simply you have to multiply all the numbers one by one, and finally you will add up all the multiplied bits. So number based conversion, from the rules you will follow is that if you want to convert from any number system to decimal, you have to multiply the coefficients with powers of the bases. And when you have to convert from decimal to any other number system, you have to use the method of division, and you will use the quotient and remainder. Also, the conversion from octal to binary and from hexadecimal to binary is quite easier. The direct conversion between these three, as we will take pairs of 3 and 4 bits. So decimal integer to binary conversion. So as I have told you that if you have to convert decimal to any other number system, you have to divide the decimal number with that base. Suppose you have to convert 13 into base 2, you will divide 13 by 2, and you will have quotient 6 and remainder 1. Again you will divide until the quotient is less than the base number. Again you will divide with 2, 2 3 is 6, and the remainder is equal to 0. Again you will divide with 2, 2 1s are 2, and quotient is 1 and remainder is 1. So finally you will have the number as 1101. 13 is equal to 1 1, starting from the last quotient to remainder is 1101. You can say you will take in this form 1101. So decimal to binary conversion in case of fractional portion. So in case of a fraction, for example we have 0.625, you have to repeatedly multiply it with the base. So first you will multiply it by 2, the integer will be 1 and the fraction will be 25. You have to multiply until the integer portion is 1 and fraction is 0 0. And if the fraction doesn't become 0, you have to take up to 3 or 4 decimal places. Again you will multiply the fraction with 2, you will have integer 0 and fraction 5. Again you will multiply 0.5 with 2, you will have integer 1 and fraction 0. Now as the fraction have become 0, you will stop here, and basically the fractional portion of binary will be equal to 0.101. In this case 0.1, you have to now take from top to bottom. 0.101. Decimal to octal conversion. Again if you have converting from decimal to any other number system. Suppose this is base 8 number system, you will divide the decimal with base 8 till the quotient is less than 8. 175 divided by 8, quotient is 21, remainder is 7. Again you will divide 21 by 8, quotient is 2 and remainder is 5. Now you have to stop here, and the number is basically equal to 257. Yes. And now if you have to convert a fraction decimal number into an octal ones, you have to repeatedly multiply it with 8 and the result is divided into integer and fractional portion. So again you will multiply 0.5 with 8. Now the fraction have become 0, so the number after decimal will be equal to 24.24 to base 8. So here's the table. As the octal number is of base 8 and 8 is equal to 2 raised to power 3, so we will need 3 bits to represent an octal number like this. So here the table we have summarized. Now suppose you have to convert directly from binary to octal, you will take pairs of 3 like this, and if there is one less 0, you can append a 0 on this side, and if there is a less 0 on this less bit on this side, you can simply append zeros also here. So you will take three groups of bits. This is equal to 110, 110 is equal to 6, 010 is equal to 2, 6 point. Again you will append a 0 here. 010 is equal to 2. So this is equal to 26.2 in octal number system. 26.2. Now this is from binary to hexadecimal conversion. In this case you will take 4 bits because hexa number is equal to 16 is equal to 2 raised to power 4. Now you will take the groups of 4 bits. So you will append 2 zeros here to make it 4 bit and 2 zeros on this side. So this is equal to 0110 is equal to 6 and 0001 is equal to 1, 0100 is equal to 4. So when you have to convert from octal to hexadecimal, simply convert from octal to binary and from binary to hexadecimal number. So this is a table summarizing decimal, binary, octal and hexadecimal. Next is topic of complements. Basically the complements in computers are used for subtraction. For example, in arithmetic logic unit there is a unit of adder, so we will use the same adder for subtraction too by using complement. When you are subtracting using a subtraction a minus b, you will simply take complement of b and add to a. So in this case, instead of making another additional subtractor, you will use the same adder for subtraction as well. So the formula for r minus 1 complement is r raised to power n minus 1 minus n, where capital N is basically the number for which you are finding the complement, and these are the number of bits in the number small n. So 9's complement of 54670 will be equal to 10 raised to power 6 minus 1 minus this number. Similarly, 1's complement of this number will be equal to 2 raised to power 7 minus 1 minus this number. So first you have to convert 2 raised to power 7 into binary as well. Another simple method to find 1's complement of binary numbers is simply convert 0 to 1 and 1 to 0. For example, for this number the 1's complement is 0 1 0 0 1 1 1. If you add a number and its 1's complement, you will have all ones in the result. Next is r's complement. R's complement is equal to r raised to power n minus capital N, where n is the number and small n is the number of digits. So the 10's complement of this number is 10 raised to power 6 minus this number, and 10's complement is 10 raised to power 6 minus this number is this. Similarly, for 2's complement, you will subtract this number from the power of 2. Another method to find the 2's complement is first you take the 1's complement of the number and simply add 1 at the least significant bit side. Like this, add 1 to this number and you will have the 2's complement finally. 1 plus 1, 1 plus 1, 0, 1, 1. 1 plus 1 0 1 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 1 0 1 0. So here are some more examples to find r minus 1 complement for base 10. If there is a fractional portion, you will have the fractional part instead of 1, because this fractional portion is basically the power of r raised to power minus 1, which is equal to 1 in case of integer. So for this number, the fractional part is the number of digit in fractional part is 0, so m is 0. So r raised to power n minus r raised to power 0 minus n is basically the general formula for r minus 1 complement, and for r's complement it is equal to r raised to power n minus n simply. So if there's a fractional portional too, here there are 4 digits in fractional part, so you will write, and there's no digit in integer part, so you will write 10 raised to power 0 minus 10 raised to power minus 4 minus this number. For this, 10 raised to power 2 minus 10 raised to power minus 3 minus this number. Same rule applies for the 1's complement in case of binary numbers.